Dear students, today we will talk about center of mass. It is a point where whole mass of a body is supposed to act. Now, consider a body which exhibits a translatory motion. By translatory motion, I mean it is a kind of linear motion where the body is displaced from one position to another. In the case of translatory motion, the various constituent particles essentially travel the same distance. Therefore, if you have to describe the motion of such body, it is very convenient to choose only one point. But if the body exhibits a rotatory motion or a vibratory motion, then we understand that not all particles of the body are at same distance from the axis of rotation. Therefore, we cannot describe the motion of this body by choosing any point because these points are at different distances from the axis of rotation. Therefore, we choose to describe the motion of this body by a point where the whole mass is supposed to act. And that point is called as center of mass. That point is called as center of mass. Remember, center of mass can be a point where actually there may not be any mass. For example, if you have a spherical shell or a ring, we know they are hollow inside. But if we have to find the center of mass by virtue of symmetry, we will easily be able to find that it is somewhere at the center. It is somewhere at the center, right? But we know this center, because it is hollow inside, there is not any mass. But even then, by virtue of geometry, by virtue of symmetry, this is the point where the whole mass of the body is supposed to act. That is why we use this word supposed to act, right? Now, suppose this is a coordinate system with respect to which we define the position of various constituent particles of a body. Suppose this is a particle of mass m1, m2, m3, m4 and so on, and their position vectors are r1, r2, r3, r4 and so on. If the center of mass is somewhere here, then its position vector is denoted by r, capital R. We define this r as m1 r1 plus m2 r2 plus so on mn rn divided by m1 plus m2 plus m3 plus so on plus mn. This is for a rigid body which consists of n constituent particles, and their masses are m1, m2, so on up to mn, and their position vectors are r1, r2, so on up to rn, right? So the position vector of the center of mass will be defined in this manner. Now we can also choose to write it in this way, that r is equal to summation mi ri, where I runs from 1 to n, obviously, divided by this. If the total mass of the body is m, we can write it mr vector is summation I goes from 1 to n mi ri, right? Now, using the same equation, we can also find the velocity of center of mass. So velocity of center of mass will be r dot, and that will be m1 r1 dot plus m2 r2 dot plus so on plus mn rn dot divided by m, this whole mass. The acceleration of the center of mass similarly will be given by r double dot, and that will be m1 r1 double dot plus m2 r2 double dot plus so on plus mn rn double dot divided by m. Similarly, the force on the center of mass can be found from the same expression. We can take this mass here, so it is F, so it is F1 So force acting on the center of mass is the sum of the forces on the constituent particles. And these are various relevant equations about the center of mass, right? Now, an important thing that you have to learn about center of mass is that the total momentum of the constituent particles with respect to center of mass is 0, right? In case of a rotatory motion or a vibratory motion, we know that the constituent particles of the body are in motion, but so they have a certain momentum, linear momentum and angular momentum. But all we have to prove is that the total momentum of the constituent particles with respect to the center of mass is always 0. So how do we understand that? We choose any particle R. So its position vector with respect to origin is R. And the position vector of the same particle with respect to center of mass. Suppose center of mass is here. The position vector of this particle with respect to center of mass is RC. And the position vector of the center of mass with respect to the origin of the frame of reference is suppose capital R, right? So if you go by the direction of arrows and you follow the triangle law of vectors, we can easily write that R plus RC is equal to R. For any ith particle, because we know that a rigid body will not be composed of just one particle, but it is composed of so many n number of particles. Therefore, for any ith particle of the body, rigid body, this equation can be written as R plus RCI plus is equal to Ri. Now, when we sum it up, that is summation R plus summation RCI is equal to summation Ri. Multiply the equation throughout by m. So summation Mi R. R is R everywhere because it is defined only for a single point, and that point is center of mass. For this R, we can write Ri because there are a good number of particles in the rigid body. So MIR plus summation of Mi RCI is equal to summation Mi Ri. Now summation of Mi will be capital M and R will be R. Summation Mi RCI is equal to, this is also MR, because we know that when we sum it up, this is equal to MR, right? It is this expression. So this is MR. M under MR will go. We are left with summation Mi RCI is equal to 0. When we differentiate it, it gives summation Mi RCI dot is equal to 0, and that is mass into velocity, total momentum. Total momentum of the system of particles about center of mass is 0. Now in certain numerical problems, you may be asked to find the center of mass of a system. It depends on the shape of system, on the choice of system, that how you will proceed about calculating the position of center of mass. Let's take a few examples to understand. For example, if I ask you to find the center of mass in case of carbon monoxide molecule whose bond length is say 1.2 angstrom units. So I'm asking you to find the position of center of mass in case of carbon monoxide molecule, either with respect to carbon or with respect to oxygen. And what is given to me is that the bond length of carbon monoxide molecule is 1.2 angstrom. So how do I proceed about it? Again, I will make use of the equations that I have derived. So I know that position of center of mass is given by m1r1 plus m2r2 divided by m1 plus m2, because in case of carbon monoxide molecule only two particles are involved, so m1r1 plus m2r2 divided by m1 plus m2. But it will be convenient for me if I choose that the center of mass is at the origin of the frame of reference, right? So I can choose, and I'm free to make such kind of choice. It is the choice of the observer, it is the choice of the analyst, wherever they want to place the frame of reference, wherever they want to place the origin, right? So I can choose the center of mass at origin of a frame of reference. So once I choose this at origin, R is 0, right? So m1r1 plus m2r2 is equal to 0. This will go here, this will again be 0. So m1r1 plus m2r2 is 0. Now, it is told that the distance between carbon and oxygen molecule is 1.12 or 2 angstrom, something. So, suppose this distance from the origin is x, that is the distance of oxygen atom from the center is x, therefore obviously this is 1.2 minus x. So we can say that R1 is xi and R2 is 1.2 minus xi, but in the minus direction, because if this is the x-axis, on the right side you have a plus value of x and on the left side you have a minus value of this component, right? And now what is m1? So m1 is carbon, right? So its value is 12. m2 is oxygen, its value is 16, and then it is easy to find it that m1, now let's give the values directly, m1 into this much 1.2 minus x times I plus m2, what is that, 16 x2 or x I is equal to 0. So you can solve it and find the value of x. It's easy, you can find the value of x. So once you find the value of x, you can say that the center of mass is at a distance this much from O and at a distance this much from C along the direction of x-axis, right? So this is how we find the center of mass. Similarly, I may give you another example that find the center of mass of a system of three particles of masses say 0.5 kg, 1 kg, 2 kg, located at the points of an equilateral triangle. Again, it will be very convenient if we choose one of the points at origin. Suppose this is the equilateral triangle. This is the mass 0.5 kg. This is the mass 1 kg. This is the mass 2 kg. They are located at the three vertices of the equilateral triangle, right? So we need to find the position of the center of mass, right? So again, the position of the center of mass will be, remember, it will be m1r1 plus m2r2 plus m3r3 divided by m1 plus m2 plus m3, because at this time three particles are involved. So I write the expression in this manner. Now what is this r? It is, for m1 you can write 0.5 kg, but its r position vector is 0 because it is located itself at the origin. So this will be 0.5 into 0 plus m2, what is another mass? It is 1. And what is its position vector? Only along x-axis, right? So suppose this equilateral triangle is of unit dimension. Suppose each side is of length unity, or 2 meter or 3 meter, whatever. For the purpose, we say for this numerical problem, we choose of unit dimension. So it will be 1 into I plus m3 will be 2, right? We don't know its coordinates now. We don't know what are the coordinates at this point, but we can help them. We can make use of this angle, right? So the cos component will be along this and the y component will be along this. We will be easily able to find its coordinates. So cos 60 is 1 by 2, I component will be this much, and j component will be sine 60, that is root 3 by 2 j. We know that all the three angles of an equilateral triangle are 60 degree. So we try to resolve this, right? So we get x coordinate as 1 by 2i and y coordinate as root 3 by 2j, divided by what is the total mass, that is 1 plus 0.5 plus 2, that is 3.5. Now this is 0, this is I, plus this is what? This is I plus root 3j. So let us sum it up. It is 2i plus root 3j divided by 3.5. So the x component is this much and the y component is this much. So r is 2 by 3.5 I plus root 3 by 3.5 j. Now if you are asked to find only the magnitude of center of mass with respect to origin, that you can find quite easily. So magnitude of r will be under root of this 2 by 3.5 square plus root 3 by 3.5 square. Whatever is the value, that gives the magnitude only of the center of mass with respect to the origin of the Cartesian coordinate system. So this is how you can face various types of numerical problems in the examination. The simplest numerical problems that you can face are of this type, that you have three masses at points P1, P2 and P3. The masses are M1, M2 and M3. Yes. So their coordinates are x1, y1 and z1, x2, y2 and z2, x3, y3 and z3. And you are asked to find the position of the center of mass. So you can write it in this manner, that it will be m1 x1i plus y1j plus z1k, right, plus m2 similarly x2i plus y2j plus z2k plus m3 times x3i y3j z3k divided by m1 plus m2 plus m3. So whatever that is gives the value of the position vector of the center of mass of a system of particles. So I hope that gives you a basic preliminary idea of the concept of center of mass. So that's all.